Okay, so in this video, I'm going to look at a few, just a few things about the Dirac Lagrangian and Dirac equation. So if I have my Dirac Lagrangian and I find the equations of motion, I do this thing. It's actually the simplest equation of motion to find because this will reduce to just the derivative of this Lagrangian with respect to psi bar. And we just have the psi bar multiplied by all this, so this equation just becomes this thing equals 0. And this is the Dirac equation. And I guess some motivation as to why this might be important: if you take the conjugate operator, so this thing, and you apply it to this equation, if you multiply, FOIL this out, you get this, and then you can replace this pair of gamma matrices with it's 1/2 plus, or 1/2 times the commutator of these matrices plus 1/2 times the anti-commutator of these matrices, and then this this partial derivative. This is symmetric in mu and nu, and this commutator is antisymmetric in mu and nu. So basically, this term will go away. I'll just be left with this commutator term, or this anti-commutator term. And we already said that these gamma matrices satisfy this anti-commutation relation, this 2 eta nu mu in this case. And so what I find basically is that each component of psi satisfies the Klein-Gordon equation. So again, psi is like a 4-component object, and so really this is like a a differential operator that multiplies a 4x4 identity matrix. So should really imagine it as like a 4x4 matrix with this operator in each of the diagonals. And so each component of psi will satisfy the Klein-Gordon equation. And then just a little factoid. So for shorthand, whenever you contract a 4-vector with this gamma matrix, you can write that as just a slash through whatever symbol you're using. So in the case of these of the Dirac equation, I have it contracted with this derivative operator. So you can rewrite the Dirac equation like this. So sometimes people do that. So now on to a little more, I think I understand what I'm about to talk about, but honestly, it's not that important. Mostly what I want to do is get to quantizing this thing and then scattering. And what I'm about to talk about doesn't really come up, or it hasn't, at least as I've seen, but it's interesting at least. And it will certainly come up, I guess, later on if I ever do an advanced quantum field theory course. So yeah. So basically, these gamma matrices satisfy this anti-commutation relation, but there isn't a unique set of matrices that satisfies this. So one that I guess we'll commonly use is known as the chiral representation, where gamma 0 is this and gamma I are these things. And again, these are 4x4 matrices, but we can write them, they're kind of blocky like this. So for example, gamma 0, when I write a 0 here, I really mean a 2x2 matrix of zeros. When I write a 1 here, I mean a 2x2 identity matrix, and so on. And similarly for the gamma i's, only this is built out of the poly matrices. So these things. And so why is the chiral representation important? Well, we'll see that once we work all this out. But basically, we can decompose our Dirac spinor into two component spinors, u plus and u minus. And then if we plug that into the Dirac equation, so this is to our Lagrangian. So this is our Lagrangian psi bars, again, psi dagger times gamma 0. So it's this. And we can just plug everything in. So psi dagger is this. It's a row matrix. And then gamma 0. And then I've split up this, I've split up the sum into the time and space part. And then I have my minus m. And I've written out, what my gamma 0 and my gamma i's are. And then size this column matrix. And so what's nice is because these are really 4x4 matrices, but because they're written in this blocky form, we can treat them like 2x2 matrices when we work this out. So I just, it's just simple matrix algebra. I multiply all this to this column vector, and I multiply this gamma 0 through, and then finally, multiply this through. And what you end up is this thing, which looks kind of ugly. But you can, one thing that's very useful to do, and that'll come up later, is you can define, I guess, I don't know if it's really a 4 vector, but I guess it's a 4, it's more of a notational thing than anything, I think. But this sigma mu, which will be, sigma 0 is the identity, and then sigma I is sigma I, and then sigma bar mu is the identity, and then minus sigma I. And if you do that, you can write it out like this. And so this is our Lagrangian, and one thing we can notice immediately is this term only involves u minus, this term only involves u plus, and then this term has both, so they're coupled. U minus and u plus are coupled through this term, but it's proportional to m. So if m is 0, then they become uncoupled, and so they are independent. So you can just work with one or the other, so it simplifies, basically. That's always useful. It also has physical interpretations later on, but I don't know if we'll talk about that or not. So yeah, if you find the equations of motion for, in this case, u plus, I did, it's this thing, and again, if m is 0, then they reduce to these equations for u plus and u minus, and these are known as the Weyl equations, or Weyl equations, however you say it. And then one last thing is that, again, this is used later. So in the chiral representation, so in this calculation, we use the chiral representation of our gamma matrices, and that's what led to these simplified equations of motion. But I guess these u plus and u minuses, they have physical interpretations. So even if you're not using the chiral representation, you should be able to have this decomposition into two this u plus and u minus. And basically, so they define this gamma 5, and that allows you to, regardless of the representation, find the, there's a term, I can't think of the name, but just basically find u plus and u minus, no matter which representation you use. So if you define another matrix gamma 5 like this, and then a projection operator that's this, then you can always find psi plus and psi minus, which is, so psi plus is just u plus and then a 0 in the bottom, and then psi minus is a 4 component with 0 and u minus at the bottom. But you just find it by projecting your spinor. It's like it projects onto psi plus to the, God, maybe I'm not saying that in the best way, but it's just gives you psi plus and psi minus. And so in the trivial case of, in the chiral representation, if you work this out, if you act p plus on psi, you'll just get, well, it just works, you just get your u plus, which is psi plus and psi minus. But basically, yeah, it's in any representation, this would still give you the chiral spinors.